This is podcast number 44, and today we're talking about alleviating the gust loading on an aircraft using rotating wingtips. So this is the aircraft that this group of researchers are looking at, and they wanted to determine if you could change the gust response of an aircraft just by having the wingtips being able to rotate. And the reason why this is important is because gusts can severely damage an aircraft and even cause catastrophic failure. At the very least, it causes an uncomfortable ride and it becomes harder to handle. So to look into this phenomenon, we're going to be looking at this paper called Gust Alleviation of a Large Aircraft with Passive Wing Tip Twist. It's an open access paper. You can find the link in the description for those of you who want to play at home. And it's quite an important aspect, and it also helps with air elasticity, which we did a podcast on a few podcasts ago when we were talking about the effects using 3D printing to better represent air elastic effects in testing of aircraft. Now, what they say is that they look into a 200-seater aircraft, so this is a typical commercial airliner. And the reason why passive twist wingtip is interesting is because you actually have this passive flow control device, and it can actually rotate independently of the rest of the wing, and it's on the very outside edge of the wings. This is usually where the ailerons are, and ailerons are flow control devices that are used to help roll the aircraft. So if you want it to roll from side to side. And with this research, they divided it into 3 different stages. So they first looked at the gust response of the aircraft with no wingtip twist, no passive flow control device. They then looked at the effects of just the wing with this passive flow control device, and then looked at the entire aircraft together with this passive wingtip twist. And they found that it is very beneficial. Like it does have legs, so it's worth looking into. And we're going to talk about more what the effects were in this paper. So they said that aircraft will be inevitably exposed to atmospheric disturbances or gusts of different degrees and severity during flight, and these gusts produce extra aerodynamic forces on the structure, especially for the wings, and leads to dynamic responses of the aircraft, such as flutter and other air elastic effects, and even just bending of the aircraft, which is bad if you exceed the loading. They say for some aircraft, the gust loads are greater than the maneuvering load and produces the most critical load on the aircraft. So you need to design the aircraft to withstand this. This means that the aircraft has to be heavier because the structures have to be stronger, and that's not good. You want it to be as light as possible. And they also say that it for civil airliners, especially with a high aspect ratio, for the wings, the gust response causes concerns for the airframe safety, ride comfort, and handling quality. The reason why that is because a high aspect ratio wing typically means that the wing is very long and very thin, and that results in a high moment arm. So for those of you who know just basic physics, if you have a bigger moment arm, if you place a load on this moment arm, you then create a greater moment or a greater torque, just simply because you have a greater moment arm, and you can break things much easier. So that's why high aspect ratio wings are particularly susceptible to this kind of phenomenon. And passenger aircraft have fairly high aspect ratio wings. They're usually around 10, 12. They're not as great as gliders, for example, at 20, but a lot more than fighter jets and far more maneuverable aircraft. So they are a concern, especially when you have 200 people on a flight. You need to make sure they're safe. And they say that the gust loads will cause an increase in the airframe weight, as we said, and reduce the structural fatigue life, and result in higher maintenance costs. And that's because you have greater structural loading, and it's a cyclical fashion. So fatigue is where you cyclically load something and then it will break over time, even at a lower loading than the maximum strength of the object, because you're continually loading it again and again, and it just eventually breaks. So it's therefore desirable to alleviate the gust load by means of an active or passive flow control system. So the active and passive flow control systems, I'm just going to explain them briefly. Active flow control systems are ones where you have a feedback mechanism, and you can change the flow control device whenever you want. So if you want it to be greater, you can change it to be greater. If you want it to be lower or have less effect, you can change that as well. Passive flow control devices are really just you set it and then you let it do its thing. It can't really be changed by you later on. passive flow control devices usually are not as effective as active flow control devices because you cannot have that feedback loop to really hone the performance of it at different operating conditions. But they are usually far more robust, so they're not going to break because they're far simpler. So that's the trade-off that we typically face. And these passive wingtip twist flow control devices are passive, as the name says. So they, in this current investigation, they aimed at evaluating the feasibility of this functional device for large civil aircraft with high aspect ratio wings. And as I mentioned, they had 3 different stages. So let's look into the gust response of the aircraft without these wingtip twist devices. So this is quite a long paper, it's about 20 pages. I don't know why they made it so long. It's like a love letter to your sweetheart. Just make 8 pages and be done with it. But anyway, so we're going to scroll through this to the juicy parts and leave out the boring parts. They say the air turbulence in real life encountered in flight is usually random and continuous in a short period. So what this means is when you're flying around, these gusts that you experience are not predictable. They're random and they can be very big, they can be very small, they can go for a very long time or a very short time. They're really just a mixed bag. So you need to be able to design for that. That's what makes them partly so dangerous. They say that this aircraft, so this one here, has a H-tail and twin open rotor engines are mounted above the rear fuselage. They say that this configuration makes the high aspect ratio wing clean for higher aerodynamic efficiency. The problem is that it's also sensitive to gust loading. So that's a trade-off. They say that the cruise speed is Mach 0.78, and that's an important thing to keep in mind, mainly because if you look at the technical data here, they say the leading edge sweep angle is only 5 degrees. That's not a lot at all. And one of the reasons why that is only 5 degrees is because it's not traveling as fast as conventional airliners today. Conventional airliners travel at about Mach 0.83, Mach 0.85. And so the reason why one reason why sweep is desirable is for high velocities is because it increases the critical Mach number. And the critical Mach number is the velocity at which over any object the flow will become sonic. For an airfoil, this is usually, well, it depends on the thickness on that, but it usually is around 0.85, 0.9. If you have a very thick airfoil, it can be even lower. So what this means, what this means is that the critical Mach number is not that high. It's not 1. The reason why is because over the airfoil, the flow accelerates. And so if the flow accelerates, even though the free stream may only be 0.85 Mach number, the local velocity over the airfoil could reach 1. It could be sonic. So the critical Mach number might be 0.85. So by sweeping the wing, you then make the effective airfoil profile thinner, and then that increases the critical Mach number, which means you can fly faster without reaching the sonic barrier and without increasing the wave drag. So that's one reason why you have sweep, and this aircraft doesn't need it as much, partly because of the lower cruise speed. Now, one cool thing they have here, which you don't see too often, is the lift distribution of this aircraft without gusts, just regularly, with gusts, and then with gusts with the passive twist wingtip. So the lift distribution without gusts is fairly continuous, and it tapers off towards the edges, much more rounded profile. And this means that you've got to get probably a lot more induced drag around the wingtips because you have more lift being produced there. And if you aren't aware of what induced drag is, it's where you have the drag being produced because of this pressure difference between the bottom surface, so usually the pressure surface, and the top surface, the suction surface. So air bleeds around the wingtip, and then it creates this vortex. The greater this pressure differential, the stronger this vortex will be, and that's more wasted energy. That's induced drag. So you don't want lift being produced near the wingtips. And interestingly, the lift with the passive wingtip twist has very little lift generation at the wingtips. So I suspect that this will actually reduce the induced drag a lot as well. So that's another added benefit of this device. Now, obviously, this is during a gust, and that's not cruise conditions, but it is still a little bit of a benefit, at least. So interestingly, the wing airfoil profile is a supercritical one, and this keeps the flow laminar as much as possible. And what supercritical airfoils look like, it's effectively a regular airfoil, but at the trailing edge, the bottom surface, so the suction surface, is just pinched a little bit. It's just pushed up a little bit, and that helps keep the flow laminar over it. And they've done some CFD showing the pressure distribution over this airfoil profile and the wing itself once you've integrated it into a airplane wing. It's quite cool. So let's look at the profile first. So the airfoil profile on the left. And what you see is on the top surface, you have a low pressure and it's fairly steady. So there's obviously a pressure gradient. It changes from the leading edge to the trailing edge, but it's not that severe. This is far less severe than actually a lot of other airfoil profiles. For example, a NACA 0012, which is like one that everyone will learn aerodynamics on. That pressure gradient is much more severe. So this pressure gradient is far more gentle, which is good. That means that you get a different pressure, a different lift generation over the airfoil. But for this type of airfoil, we want to maintain a laminar flow. That's quite nice. Then on the right, we have this airfoil incorporated into the wingtip, into the wing itself. And again, you get a fairly nice, gentle gradient for this pressure. It's not very sharp. And then they also plotted the shear force acting on the wing of the aircraft and the bending moment. And as you can expect, near the wing root is where you get the greatest shear force and the greatest bending moment. So that's where the wing is probably going to snap if you overload it. So that's not good. You don't want wing snapping. One thing that they looked into here, which I haven't seen too much, and it's quite nice to see every now and then, is they have the wing and they break it down based on the weights of the different components. So, for example, the winglet, they say is only 11 kilograms in weight. The overall weight of the wing is 1,436 kilos, so 1.4 tons. Now, interestingly, for this aircraft, they adopted an interesting method, which is where they made the skin somewhat load-bearing. That's not typically the case in regular aircraft, but they made the thickness of the skin up to like 20 millimeters, so almost 1 inch thick at the wing root, and then like only a few millimeters thick at the wingtip, like 3 millimeters. So the skin is actually taking some of the loading, and that's not very common. So the lower skin is actually 264 kilograms in weight. So that's a lot. The upper skin is 259 kilograms. Again, that's a lot. The front and rear spars, which are typically the massive load-bearing structures of an aircraft wing, are only 29 and 24 kilograms. So that's very light. Usually, like in terms of the skin weight and the front spars, the spar weights, they're usually the opposite. So the spars will usually be a lot heavier than the skins, but in this case, they've reversed it just based on this funky design. Then you have the ribs, which are 24 kilos. Again, that's very light. And then the leading edge is only 19 kilos. So this weight breakdown is quite cool to see. You don't see it too often. So I thought I'd just cover it here briefly. Now what they looked into, as I mentioned earlier, the loading on the wing without these wingtips. And what you can find here is, as you'd expect, the maximum stress and maximum strain occur at the wing root. So this is where the wings are usually going to snap off. Then they looked at the wingtips with these passive twist flow control devices, and they looked at the gust response of these. So they said that these passive twist wingtips are separate wing segments mounted at the wingtip through a shaft and a torque spring connected with the wing's front spar. And they have a figure here. So they have the rest of the wing, and then there's just this rod coming out, which then connects to this wingtip, and it's the entire wingtip. So it's the entire cord. It's not just the back half. It's the entire wingtip, and that this whole thing rotates. And one really cool thing that they have is the point at which it rotates about is quite close to the leading edge. So that means that when you have positive lift generation, this wingtip part will rotate downwards. So that means that this wingtip is then producing negative lift, and then it's going to be pulling the wing down. So that's why it's beneficial in terms of stabilizing this gust response. Now, they have this wingtip attached to a spring to then be able to control how much this wingtip deflects, how much it rotates down. And this spring stiffness changes with deflection amount. They say that the basic requirement for the torque spring is set to be stiff enough to maintain the designed aerodynamic angle of attack of 3.7 degrees under a 1G level flight in cruise. So in other words, during cruise, this wingtip is expected to stay at 3.7 degrees angle of attack, and that's what they need for just to maintain cruise. Now, the spring is stiffened to achieve that. However, when you have a gust, the wing is obviously going to be producing more lift than that, and it's going to be wanting to rotate down because this lift is rotating about this axis and then it's going to rotate around. I think earlier actually I said that's going to produce negative lift. That is the case when it rotates around. Yes, that's right. I just wanted to make sure I said that correctly. But coming back to this, once it rotates, the spring stiffness stays fairly constant, so it can rotate to a certain amount. And then once it hits a certain angle of attack, the stiffness then increases dramatically, so the wingtip cannot rotate anymore. And what they say here is under extra lift due to gust, the maximum twist angle of this passive wingtip is limited to minus 10 degrees to avoid stall. So that's what this massive increase in spring stiffness achieves. It stops this wingtip being able to rotate more than minus 10 degrees to prevent stall, and then if you have stall, then that's going to produce a massive loss in force, and that's going to result in the wing all of a sudden popping up, and that's going to be very hard to control, not to mention very dangerous, because then you're overloading the wing potentially, and then the wing will snap off and the pilot can't do anything about it because it was so sudden. And even if they could do something, even if it was gradual, they still really couldn't do much because, well, the wing is already overloaded and they don't have the flow control device to help it. So that's why you really want to stop this from happening. And that's why they made this spring very stiff. So it's a very clever design. I'm quite impressed. It's a little bit out of the box. And they say within the range of the spring stiffness from K equals 0.1 to 10 kilonewton meters per radian, the this passive twist wingtip torsional frequency increases from 0.034 to 0.173 hertz. The reason why this increase is important is because it says that the coupling can be avoided between this wingtip and the bending mode of the wing. That's very important because you don't want coupling to occur between different bending and torsional modes. The reason why that is because if they do couple, then that can magnify forces and create catastrophic failure very quickly. What's more, it can also just create a more complex way that this wing is interacting with the air, and then you need to calculate this properly to take it into account. It becomes much harder. It's very complex. So by stopping this coupling occurring, you can then make the vehicle safer. So they go on to the critical flutter speed. So Flutter, which I covered in that podcast talking about 3D printing for aeroelastic purposes. Flutter is where the wing will start vibrating and then it'll get more and more violent to the point where the loading is just so great that it'll snap off. And that's not good. Airplanes are supposed to have wings. And this critical flutter speed is 283 meters per second. It needs to be at least that, which is 15% greater than the dive speed, according to requirements by governing bodies. Your flutter speed for a airliner needs to be above this to make their vehicle safer. What they found was that the flutter speed of this wing with this passive wing twist of 30 kilograms mounted to this shaft with this spring stiffness is 300 meters per second, so it's well above the requirement. So that's quite nice. It meets the requirement then. Interestingly, they have the effect of the weight of this passive wingtip twist, its effects of the weight on the flutter speed. And as you increase the this weight, the flutter speed dramatically drops. So at 30 kilos, you're well above, you're at 300 meters per second. But at 60 kilos, so double, the flutter speed is now dropped to like 125 meters per second. So it's terrible. So you want to keep that wingtip as light as possible. They then said that from the results, it's noted that the passive tip wingtip is generally more effective when the gusts have larger gradients and are lower in frequency. So that makes sense in terms of the frequency because this is an object that has a second moment of inertia, so it has just inertia in general. So it can only react so quickly. If you have a very quick gust, then this doesn't have a chance to react as well as effectively. So having a lower frequency means that it has more time to react, which it can do effectively. So that makes sense. Now, they move on to the gust response of the entire aircraft, not just the wing. And this is important. So they have the gust response of the center of gravity and the wingtip deflection of the baseline aircraft without this wingtip. And what they find is that the wingtip displacement is quite large. It goes up to 80 centimeters, so 800 millimeters, and then it shoots down. So there's like this overshoot when it recovers when you see a gust. So what happens with the gust is this wingtip massively heaves, and then it dives down, and then it comes back to zero. And they say, comparing with the previous results of the wing alone, the gust loading on the wing was largely reduced, with the wingtip deflection reduced by 48%. So in other words, when you're just looking at the wing without the rest of the aircraft, the deflection of the wing is greater, and that's because nothing else is absorbing the energy from this gust. It's just the wing. However, when you have the aircraft attached to the wing, the wingtip deflection reduces by 48% from 1.6 meters to almost 0.8 meters, half. And this is because the gust energy was absorbed not only by the wing elastic deformation, but also by the potential energy of the aircraft moving upwards. And it moves up by 8 meters, so a massive amount. It's like you jump up 8 meters, which is why when you're in an aircraft and you know how you get those gusts sometimes and it feels like being kicked in the pants? That's why the aircraft has jumped up a couple meters and you're left thinking what you did wrong. Anyway, comparing with the gust wingtip deflection, the strain under the static ultimate load indicates that the gust load in real life actually reaches 46% of the ultimate load, and this is putting the structural integrity at risk. So in other words, we're loading the wing to 46% of the ultimate load, so the point where the wing will fail, and that's starting to get a little bit close for comfort. They say in comparison with the baseline results, it can be seen that a significant reduction in the wingtip deflection by 21% is achieved when you put these wingtip devices on. And it also shows that the elastic twist angle of the wing reaches almost minus 9 degrees in response to this gust loading. So they have these graphs here now, and the wingtip deflection has dropped by 200 millimeters, and it doesn't have as much of an overshoot either. So that's quite nice. It means that it's working. They also say that the bending moment at the wing root is also significantly reduced by 10.6%. So that's quite good. And they say that the gust-induced extra loading on the wing can be reduced from 46% of the ultimate loading to only 36.5%. So again, you're making the aircraft safer by having these wingtip devices on there that can rotate about this rod. Comparing with the baseline aircraft where the maximum load in the most critical gust exceeds the design ultimate load by 15.7%. So what I mean is when you're just looking at the wing itself with no aircraft, without any wingtip either, the the gust load exceeds the ultimate loading by 15.7%. So in other words, it's going to fail. Whereas when you have the wingtips on here, it reduces the maximum aerodynamic load below the ultimate load. So now it's not going to fail. And this just reminds me of one time I was looking at this vehicle. It was actually a little race car that some engineers had made to enter a state competition, and they were designing it, and they designed the safety factor, which is the factor that you apply to whatever you're designing to have a little bit of wiggle room, so it's safer. They designed the vehicle to have a safety factor of 0.7, which is below 1, which means that throughout the operation cycle of the vehicle, it will break. And for some reason, they thought that this was a good idea. I don't know why. So I don't know if it was me or someone else, we told them, well, you really have to design it to have one or more, because what you've done here, it means that at some point during your lap, the vehicle is going to fail, and it's probably going to fail at a speed which is not 0 kilometers per hour, because that's where the force is going to be greatest, at not 0. It's going to be at maybe 40 or 50 or 60 kilometers per hour, and you don't want your vehicle to fail at speed because that's dangerous. So that was quite funny when they thought that a safety factor of 0.7 was appropriate. And that's just what it reminded me of there. Anyway, I just want to quickly say to check out everything to Aerodynamics, check out the instrumentation we do. So we do instrumentation, which is the Atmosphere Hawk. This is a device that will measure accurately the temperature in your wind tunnel or whatever experimental facility you have. It will accurately measure the barometric pressure and accurately measure the humidity. The reason why these three parameters are very important for your experiments are one major reason is that they affect the density of the air that you're using. This density then will affect the velocity that you're calculating. It will affect the non-dimensional coefficients, such as the drag coefficient, lift coefficient. It will affect the Reynolds number, and so on. So if you don't accurately measure the density, you're getting errors in these values. And the worst time is when you don't even know that you have these values, these errors in these values. Then when you try to validate any CFD that you might do, your density is going to be different. So your drag, your lift, and all that are going to not line up. That's going to give you headaches. The Atmosphere Hawk gets rid of that. So check that out, link in the description. We also do PIV and traverses, and we also have a new flow visualization technique. It's called the Rayleigh scattering flow vis technique. We're getting that up and running as well, so stay tuned for that. Also check out the courses we do here at Aerodynamics. We do CFD, we do experimental, and we do theory like this, so you can get better at aerodynamics. And we also have the International Aerodynamics Conference every year. There's a conference every year for aerodynamics to get together and talk about aerodynamics. Links in the description. So let's get back to this podcast, and let's sum it up now. So they say, and also make sure to like and subscribe to this, because it helps you out, helps us out, and you get more aerodynamics in your life, which everyone loves. So they say that, back to the paper, in the most critical gust load case, the maximum aerodynamic loading on the wing can exceed the ultimate load by 15.7%, and this causes structural integrity problems. However, with the passive twist wingtip, it reduces this loading and gets it to below this maximum ultimate load and makes it safer. They also say that the significant gust response alleviation can be achieved by employing this wingtip in the whole range of gust gradients specified in the airworthiness standards. So in other words, across the board, these wingtips are good. They will help. In the most critical case, the gust-induced wingtip deflection and bending moment at the wing root can be reduced by 21% and 11% respectively, so a huge amount. That means that you can make the aircraft lighter and also make it safer, which is good for range and fuel usage, fuel economy, and ride comfort for the passengers. You don't want to shake them around like they're in the paint shaker. You don't want their brain scrambled. You want them to be nice and happy. They say, consequently, the maximum load, including the worst gust load on the wing, can be reduced by below the design ultimate load by employing these wingtips. They also say that these wingtips influence the symmetric maneuvering of the aircraft in terms of normal velocity, and heaving motion is negligible. But the influence of these wingtips on the unsymmetric maneuvering of the aircraft raises a concern with the roll moment and roll rates. They're reduced by 20.5 and 12% respectively. So what this means is the rolling of the aircraft is not as effective anymore with these wingtips. Now, that's not necessarily that bad. I mean, as an idea, for commercial airliners, you don't want the aircraft to be very maneuverable. You want it to be very stable. You want it to be like a sofa in the air, just very comfortable. It moves gently, and the people on board are very happy. That's safe. That's happy. However, there are standards that you need to meet in terms of the ability to roll. And if you drop these roll moments and roll rates by 24.5 and 12%, that's probably going to be below these standards, and you need to then make these ailerons bigger to then be able to offset this problem. So that's one thing to look out for. Finally, they say the investigation has shown that the passive twist wingtip is a reliable and effective means for gust alleviation and has potential for large civil aircraft. So that's the end of this paper. Make sure to like, subscribe, and share this with your friends if you have friends that want to get better aerodynamics. Some friends, are very ordinary. They don't want to get better aerodynamics. Leave them be, but get your friends who do want to be better aerodynamics. Show them this. And check out what we do at Aerodynamics. Check out the instrumentation we do. Check out the courses we do. And check out the conference, and check out our other podcasts. So see you in the next podcast. Peace out, amigos.